Hey everybody, this video is about drift velocity. Drift velocity is a question of how fast the charges shift as they travel through a wire. Because what we've got here are these little positive charge carriers. Positive because I am talking about current, and I've drawn these little dots as places where electrons are not. Little positive charges that are shifting to the right as electrons shift to the left. And they are doing that at a speed. And when you watch, if you were able to shrink down to the size of an atom and you could watch these electrons shift to the left, charges shift to the right, you would see them bumping around each other. They'd be traveling at huge velocities into each other. Big collisions happening, and there would be, though, a little bit of shift to the right. You'd notice as you watched and waited that over time, like slowly, these would be moving to the right after every single collision. Sometimes they might move left, but overall, a shift to the right, that's called drift velocity. And we can derive that idea with knowing a few things about this wire. First, we need to talk about the idea of just current in general. That current is the rate of flow of charge, dq dt. Or I could say delta q over delta t, because I'll just use algebra ideas for this one. And here, those charges in there, how many there are is something I can actually count. I can do that if I know the volume of this conductor, which I will say V. Don't confuse that V with potential or velocity. That is an uppercase V. That is a volume right there. And if I know how many electrons there are per volume, that is a symbol N in physics. The number of free, I'll say charge carriers, because I'm talking about the positive charges that are going, so where the electrons aren't, per volume. And if I wanted to relate that to delta Q, I could just multiply that by E, the elementary charge. That smallest amount of charge we found in Millikan's oil drop experiment. 1.6 times 10 to the negative 19th coulombs. That's all equal to delta Q. This is just a density, that is a volume, and that's charge, because we're talking about like an actual charge. So microscopically, that's what makes up this delta Q that's flowing to the right. If I plug that in here, V times N times E, all over delta T. There's a few things. One thing I want to do is mess around with this V. Instead of a volume, I want to talk about the cross-sectional area multiplied by the length. And all of that is equal to the current right there. And here, the special thing is going to happen when I look at this L and this delta T term. That is our drift velocity. That's V sub D. How fast they're traveling horizontally, that length divided by that time, is the drift velocity. So we did it. We looked at Ohm's law, or the flow of current, and we looked at what was happening on a microscopic scale. So that's equal to, I can do this, N times E times V sub D times A, and it makes a fun little expression, I never. Neat things about that is that the drift velocity is directly proportional to the current, which kind of makes sense. That the faster they're going, the more current you've got. Also, what kind of makes sense is that the number of free electrons per volume is also proportional to the current. And that kind of makes sense, because if there's more free electrons to move at that velocity, there should be more current. And what also makes sense is that area is proportional to the current. Because if there's just a bigger area and a thicker wire is going to have more current, because if there's the same number of electrons per volume traveling at that constant velocity V, then that's what more current is going to be, more charge per time. So that equation, that's how we write that one. Sometimes you see it in terms of the current density, where you divide the A over and you get J equals NEV sub D. But that's the way it's written on our equation sheets. And there are some great mastering physics questions for you guys about this relationship. See ya!